I'm the guy that has to follow Dr. Buchanan, so pressure's on me. But so quick intro. My name's Hansang. I work for Citi, formerly known as Citigroup, and I have a couple different roles at Citi. I own some of the network management tools that we have, faults, alerting, capacity management. I also have another role where I have a team of people that troubleshoot application and network issues. So over the course of the year, I always cherry pick these interesting problems that we see on the network, and I squirrel them away for a presentation at SharkFest. And so everything that you see here happened in real life. It was a real life troubleshooting, and I kind of show you how we use the different tools, and Wireshark in this case, to solve these problems. And the title, Packet Trace Whispering, seems kind of hokey, but the reason why I chose that is because some of these problems are kind of simple. Right? If you're an expert in doing protocol analysis, a lot of this should jump out immediately, and you can resolve them. What I found though is if someone who's an expert in protocol analysis takes 2-3 minutes and says, "Oh, here you go, here's the problem," to someone who's not very well versed, it can take hours, right? Because you don't quite know what to look for, right? And that's fundamentally, there is no Google for Wireshark, right? You can't just type some search terms and tell me what the hell's wrong. That button hasn't been So one of the things that I do in this session is I show you some of the newer features of Wireshark that I had nothing to do with, but I'd like to thank the developers, the core developers that keep adding functions and features. And one of those that I'll use in this presentation is quite useful, right? So I'd like to show you some kind of the tips and tricks of the trade when we do the packet analysis. Okay, so the first one, pretty routine. We put in new routers, new infrastructure into a data center, and the application folks call and say, it's not working. So most of you are probably, I'm assuming, routing and switching type people. Of course, the first thing is the network's not working. And then we always shoot that with, the application's not working. But when there's packet loss, and it's bursty packet loss, it's not kind of a black hole, but kind of just bursty packet loss, chances are it's the network that's doing it. There's either buffer starvation, there's congestion somewhere, so it's probably the infrastructure. So more than any other type of problem, when you have packet loss, you need to start looking at the network as the usual suspect. Okay? So in this particular case, a new international circuit, new data center, they're doing testing, and sure enough, something doesn't work. And it was a Unix-based that uses SSH, you know, log in, get some interactive screen through SSH tunnel, etc., and it's not working. So they were troubleshooting for about 2 weeks. Finally, it kind of goes up through multiple layers, gets to my application performance team to look at. And so let's take a look at the trace itself. So I get an email, Hansang, this isn't working, can you help? So he said, all right. So you bring up Wireshark, and notice what I have here, right? So this time column here is the default time since the beginning of the packet picture, very useful. I also add the delta column here directly. Now, you can actually change this time field that comes up as default, and you can come up here under View and Time Display Format and change it to whatever you want, okay? But I also like to see in context, and I'll show you why I do this, the separate column for delta and time. I also like to see the length. So this is actually, for me, it helps quite a bit when I'm troubleshooting because things will start to jump out at you, right? So one of the things about protocol analysis is really, it's looking for patterns. And I repeat this every year, but if you look for patterns, your brain has this incredible power to filter out things that don't matter, and it'll start to, your eyes will automatically focus on something that doesn't seem right, right? And it only comes with practice. So one of my colleagues who's here, actually is in the basic course, said, when he opens up Wireshark, he opens it up, he stares intently at the screen, but don't know where to go after that, right? Because there's a lot of information here, right? And he said, you know, I usually open up all these tabs, and but I don't really know what I'm looking for, right? So the goal of this session is to help you guide and kind of shine that big spotlight to problems. So the first thing I do, and I'm kind of giving you what we do when we do troubleshooting, and the first thing that I do without fail is this. I'm looking for flags or TCP behavior that Wireshark thinks is wrong. And clearly, we have things that show up. Retransmission. So what causes retransmissions? It could be congestion, it could be packet loss, it could be a lot of things. It could be fake packet loss too, right? And in last year's session, I went into some where the monitoring capability caused Wireshark to think packets were lost when in fact they weren't, right? And there are some ways, tips and tricks to figure that portion out. And if you go to the last year's session, I dealt with that. So, what's the first thing that pops up in this screen? Someone kind of describe what you see on the screen. Again, this is all about picking up patterns, looking for commonalities, etc. Give me some, anybody?
Close together.
I'm sorry, you're going to have to speak up, I can't.
They're all close together.
Okay, so they're kind of close together. How do we know that? We got the packet numbers here, right? So we're losing in bunches, right? Because you see this here that it's not jumping all over the place. What else? I'm sorry?
The delta's probably pretty big.
The delta, okay. So look at the delta here. 2, 5, 10, 20. So when you're doing protocol analysis, there are certain numbers and boundary conditions you should look for, right? Certain numbers, right? And everybody that's done comp sci, whether it's based on 1024, multiples thereof, 2 to the 4, etc. These types of back-offs are clues to what's going on, right? So when you see this doubling of delays, it's a big clue that something is going wrong, and it's not artificial. It's typically the protocol doing it because they're built to back off, right, and keep waiting, exponential back off, etc. What else do we see here? Retransmission. Retransmission, right? Clearly it's retransmission. What else?
Same source,
yeah, so same source destination, one direction, right? So immediately that jumps out at you. So what you need to do is you need to file this away and kind of process it and put it in the background and start to, and as you do your troubleshooting, things will start to emerge. Okay, so first, this is as good a place as any to start. I'm going to clear this out. So let's do quick analysis. And this is something that trips up a lot of beginners when you're doing protocol analysis, that TCP is a two-way conversation, right? Most people concentrate in one direction, and in file transfer, it almost is just, file packets going in one direction with acknowledgments going in the other. So we're going to jump up here and take a look at some things, okay? So the first thing I'm going to do is this retransmission. Wireshark clearly says it's a retransmission, and let's take a look. And it says sequence number 2401. So Wireshark tells you that I'm starting at 2401 and I've gone as far as 3329. Okay? And all that is I started at 2401, this is my left edge, I've sent 928 bytes, and that adds up to 3329. Okay, that's all that means. So if you're doing like video and editing or music editing, all it is that slider window that you move around so you can bracket where you're looking at, right? Remember, TCP is a streams-oriented protocol. There is no start and end. It's just constant streaming of data. So all this is telling you is that I'm starting at this 2401 byte and going up to 3329. Okay? So this is a retransmission, which means previous to this packet, there should be what? Original packet. So how do we find it?
The sequence numbers.
And sure enough, we see one here with the sequence number 2401, but what's different about it? I'm sorry? Smaller size. Is that a problem?
Well, your retransmission should be the same size as the original packet.
I'm sorry,
Shouldn't the retransmit be the same size as the original packet?
okay, so shouldn't the retransmission be the same packet?
TCP is not doing retransmission. It's not a TCP retransmission.
It's not a TCP retransmission is one answer. Well, clearly it is TCP and it is a retransmission, right?
But it's not the TCP on the host.
It's not TCP host that's doing
It's
it?
not the TCP it's on the host.
Okay, all right.
Necessary.
So this is something that'll trip up people who say they know TCP, but don't really understand TCP. And the goal of this class is really to get you to think about what's happening in the background, right? So what's TCP's job? The textbook answer, TCP versus UDP. TCP is guaranteed delivery. How does it guarantee the delivery? Acknowledgements, okay. What else? It sets aside buffers, right? Because think about this, right? And you have to kind of go inside the stack to do this, but you're the TCP engine, you're the stack. The application gives you packets to send, okay? Once you get that, you have to set it aside into a buffer and you send it. And when you get an acknowledgement saying, hey, I'm getting the system, I got it, I can throw it away from my buffer and get some more information, right? Because if that packet gets lost, I can't go back up to the application and say, hey, sorry, I lost that. Could you go back in time and send me that information? Applications can't do that, right? So your job as TCP to set aside that send buffer, hold on to those packets until you get a positive acknowledgement that the packet arrived. Okay, it's very simple in concept, but you have to think. So let's kind of take that logic and figure out what's happening. Here's our first packet that starts with 2401 and has a length of 88. But this retransmission is 982 bytes. What happened? Data.
More data got into the sender's buffer.
More data got into the sender's buffer. Why? Because TCP is streams oriented, right? There is no start and end. So, I sent the first packet with 142 bytes. Why? That's all I had in my buffer. Okay? So notice the time here. It's 2 seconds is an eternity, right? From a network standpoint, 2 seconds is eternity. So while I'm sitting here waiting for this packet, an acknowledgement to come back, the application gave me more data. So when I'm ready to retransmit, because no one told me that this packet here, 2401, starting at 2401, I never got an acknowledgement that the other side received it. So instead of retransmitting packetized format, in other words, instead of resending this exact packet with 142 bytes, I have more stuff in my buffer, I might as well send it. Right? So the thing that you have to pick out here is that just because you're looking for a retransmission, the packet sizes may not be the same, and it's not a problem. It just means that TCP is doing its job and being efficient. Okay? What else can we look at to troubleshoot this? So we have retransmission. Why? That's the question. Everybody knows it's retransmission, but why? That's your job to find out. So there are some clues that you can use to figure out this problem. Okay? The first one we're going to do is look at the Reddit stepchild of Wireshark, the IP header. Everybody looks at the TCP, everybody's doing sequence analysis, and a lot of people forget that IP layer actually is there for a purpose, right? So let's take a look. And so I'm going to clear this out. Into packet 113, it's just an acknowledgement, right? So what does this acknowledgement tell us? That we're all caught up, right? Acknowledgement means I'm up good up to this point in time. Okay, so the source 10 is saying, look, I'm good to 1312. I got that. My next sequence number that I'm going to start with is 2401. And we go to the next packet, and sure enough, he starts with 2401. That's where I left off, and I'm going to send you 80 bytes worth, and that's going to come out to the next sequence number, 2489. So if you actually add up this packet 114 through 120, okay, and you add up the length, you actually come with 982. So everything's working as designed so far. Our only problem is packets are not getting through. So what happened? So let's take a look. I'm going to open up the IP header, and this whole section, I keep going back to the IP ID field because it can help you in your analysis. Okay, it's not a guaranteed way of doing analysis because IP ID turns out not required. They can all be zeros. Okay, some systems increment by 2, Some systems increment by 1. So you kind of have to get a feel for what you're dealing with here. So one of the new features that Core Developer added, which I'm forever grateful for, is applying this as a column. Okay, so I pick the IP ID field and apply it as a column, and instantly I get IP IDs all lining up here. Okay, for this packet. So what do we see here? Describe to me what you're seeing. Things that should jump out at you. I think I heard the answer here.
Sequential.
They're sequential, right? So if you look at this, it's F1, F2, F3, F4, and if you actually scroll over more, they're in decimal. Okay? What does that tell us?
Nobody else is using the NIC.
Nobody else is using the NIC. Why is that?
Nobody else is using the NIC for IP.
Yeah, for IP, exactly. Why is that? Because IP is not unique to that TCP conversation. When you have multiple TCP conversations, they're all using the same IP stack. Okay, the difference, FTP, Telnet, SSH, they're all going to take this IP ID and use it up. But if it's sequential like this, you know there's nothing else going on this box. Okay? What else does it tell us?
During your retransmissions, there's other things occurring.
During retransmissions, there are other things occurring.
Your PID increases quite a bit.
Okay, but they're all going up by 1, which means that between this packet and this packet, the 10 dot guy was doing nothing else from an IP standpoint. Okay? So is the packet loss before we got to this packet trace where we captured this, or is it past it? So I'm capturing at a certain point in the transmission. Am I seeing the packet loss before or after? It's after. So now I kind of divided my problem, so I don't have to worry about all the infrastructure from where I captured it to the left side. Because this IP ID here tells me I got everything in a row, nothing's wrong. Okay? So now we see this exponential back off that we saw when we looked at the delta, right? Two, 5, 10, 20, 40, 49. IP IDs. What's happening here?
Jumping.
Because in between this backing off, something is going on, right? So again, this is all about identifying patterns. So I got this packet and I'm scrolling down, right? And something jumps out at me.
Roll again. Don't.
Same
The
like
flags change.
I'm sorry?
The flags?
The flag is changing?
You go back up to the top one, wasn't it don't fragment?
Okay.
Yeah. Goes from don't fragment to 0.
Okay. What else? Again, when you get used to the tool, this will jump out at you like a spotlight. But if you're not used to the tool and you're not used to seeing it, it's very hard for your brain to process. So when I first got this, we opened it up, and within a matter of seconds we said, oh, here's the problem. Potential problem. We weren't sure.
Is it burst? Packet burst?
Bursting, possibly, but look at the back off, right? Clearly, there's nothing, huge gaps of time here. What else jumps out? In the middle of the screen, what does it say?
Keep scrolling, I can't see a pattern.
It's okay, it's fine. Just right in the middle of the screen, what does it say? DSCP, what does it say about the DSCP value? I'll give you the answer. Unknown DSCP. So what does that mean? So for those of you that are not familiar, and actually Dr. Ken alluded to this, diff-serve code points are common and they have specified values, right? And these are the DSCP values that packets can be tagged with. And you can spend a whole class on it, but it started out as kind of a toss bit, and there are a limited number of bits in an IP and TCP, right? So people keep retrofitting different meanings to them. And going from IP precedence to DSCP, there are certain values within an IP header that tells you what the DSCP is. And these are the well-known ones. So, for example, most of you might have heard of EF, expedited forwarding, that voice uses. Right? There's a bunch of AF classes, CS classes, etc. So here they are, right? Expedited forwarding, CS5, etc. But our DSCP value is not one of them. So is that a clue? Possibly. So what did I say when I got this packet trace? I said, well, I'm not sure, but I think this is the problem. And they said, what? I said, we're going through a carrier cloud, and we're giving them a packet with an unknown DSCP value, right? We're not playing by the rules of the game. So my assumption was the carrier, when they saw this DSCP value 04, nonsensical, they're throwing it away. So how do I prove that? How do I prove it within this trace?
Look at the packets that succeeded.
Look at the packets that were going through before, right? Because clearly we didn't start out with just this where nothing was getting through. So let's go back in time and take a look. I'm going to scroll it up. Did you see a change? That's the default. Default is 0, right? And look what happens. If you go through this analysis, the minute the DSCP value goes to 04, nothing goes past after that. So you add this length 142, 266, 122, etc., you end up with 982. So everything that was tagged as 04 didn't get through. Pretty simple problem once you know what to look for, right? So this isn't a difficult problem to solve, but this is a difficult problem to figure out when all you have is Wireshark as your tool, right? And it's about pattern recognition. So as you go down here, and I do this quite often, I get to a problem point, right? So with TCP analysis said that right here was when the retransmission started occurring. I found the beginning of the problem, packet train if you will, right? And I just kind of scroll down and see what changes. And more often than not, you'd be surprised how often when something changes or flashes in the screen, your eye automatically gravitates toward it. And if you know what you're looking for, you're going to spot the problem. So how did we prove it? Well, we did this. So I told my colleagues in Asia Pacific, Cisco routers, you can ping, right? But you can do an extended ping, and you can do all kinds of different things with it. And one of the things that you can do is you can go to extended, just by typing ping IP, target, usual stuff. And then when you get to the extended command, you say yes. You can give it the source, and then you can give it the type of service. It doesn't say diffserv or DSCP, it just says type of service. But if you go back to my chart here, right, we have type of service that maps to DSCP. It's all the same value, right? Originally this type of service, then became DSCP. So you can specify different value, and sure enough, when we specified a nonsensical number, nothing went through. When we specified it with default, everything went through. Okay? So proof positive that the carrier, because this is my, this router here is my entry just before the cloud, and this router is my, actually the target here, is just the other side. Okay, nothing's between me except for my router, carrier's router, the cloud, and then my router on the other side. So proof positive that the carrier would propagate. Okay, not their fault really if you think about it. But fundamentally I had a problem, and that is, one of the things that I learned was, especially when you're doing hardware designs and whatnot, is you have to be strict in what you send out. Right? It's under my control, I'm going to follow the rules, and I'm going to be very strict and not send out garbage that doesn't follow the rules. But when I'm receiving, I'm going to be very liberal. Why? My assumption is everybody else is stupid. Right? They may not follow the rules. So in other clouds, in other carriers, this didn't happen. Do I blame the carrier? Not really. It's a nonsensical value, but then at the same time, what do they care what my TOS bits are set to, right? Well, actually, it turns out they do care. Because now with MPLS, they charge you based on different class. So voice class is more expensive than default class. And they need to measure you. So if they, from their standpoint, hey, this doesn't follow our contract, I said I'm going to give you these 4 queues, it's outside of that, I'm going to throw it away. Okay, so any questions about that so far? Yes?
What was causing the change along the way?
So what caused it to change along the way? Good question. I didn't get into it in detail, but if you noticed at the beginning, this is a what kind of packet? SSH, right? And SSH has 2 different roles. One, file transfer, right? You can SCP, SFTP, etc. Or it's interactive, like Telnet. So if you Google for this, there's actually a setting that says, somebody figured out that, you know what? I'm going to differentiate between a bulk transfer and an interactive, and I'm going to use 04 as my diff serve. The fact that it doesn't exist was kind of unfortunate, right? But the idea here was that SSH, the application, wanted to differentiate Telnet-like behavior and transfer behavior by using a different diff serve code point.
OpenSSH did that, or your client?
SSH did that. Okay? And so this is a case of, well, we did trust the server port. We were going to accept whatever markings were coming out of that port because we didn't put QoS on there yet. And this is one of very few cases where the application did change the QoS value. And that got us into trouble.
You guys just end up remarking it? That's when you send it through?
Yeah, so that's one of the ways you do it is you strip it away. Say, I don't trust you. I'm going to mark you based on my rules. Right? If you're a via Cisco phone, I mark you EF, everything else, default. If you're FTP, bulk transfer, etc. Okay? So there are different ways from a network standpoint that you can deal with to get over this problem.
Did that break SSH on the other side?
Did it break SSH on the other side?
Yeah, so when it's expecting the disk value to be that 04?
No. Surprisingly, well, we don't know because the packets never got to the other side. Right? But I don't think the application cares too much about this server. Because by the time the application comes up to the stack, it's all stripped out. Right? The application doesn't know about diff serve code points. It's the stack that's doing it. Right? Okay, so kind of a simple example. So any questions? Anything else? Okay. This next example is also simple, meaning the problem statement is simple. Right? But what we need to do is we need to coax different information out of it. And if you've noticed, all the presentations I've done so far, it's always been, the application is broken, the network is fine. But now this is another case of, do I have more network problems? Again, it's packet loss. It was on a very high-profile platform, right? Kind of the platform that, if things go wrong, people scramble because millions of dollars, tens of millions of dollars, if not hundreds of millions of dollars go past this network. So clearly, when we have an issue, it's all hands on deck, and this is one of those cases. So, packet loss. Let's open up the packet trace and take a look. All right, so what do I do first here? Let me get rid of this IP identification field for now. What do we type? What do we see? Retransmissions. Are they real? Probably, because I see more than one, right? By the way, there was if you see massive amounts of retransmissions, or massive amounts of packet loss, or out of sequence, or duplicate acknowledgement, and I'm talking massive, basically every other packet, right? Then suspect the capturing methodology. Because very few applications work when every other packet is getting lost. So more than likely, it was you captured it at 2 different points, merged it, and you're seeing the packet twice. How do you prove that? You look at IP ID field. If it's got the same source destination and IP ID, it's the same packet, 2 different parts of the network. Okay? And if you look at the TTL, which I'll show you an example of, you can even figure out how far apart that capture point must have been, because you can use a TTL filter for that. All right? So what's different about this screen from the previous one?
Bidirectional.
Bidirectional. So our number one clue is, oh wait a minute, I don't have a one-way packet loss, right? I'm seeing a two-way conversation, and I see my source and destination changing. What else do I see here? So let's go down the list. Let's open up the TCP and look at the sequence number, 2904, 2904, 2904. But what else is happening?
The length is growing again.
The length is growing again. So is that a problem? Well, no. We just learned that's fine. My buffer is growing. I didn't get an acknowledgement. I'm going to just give you more. Okay? Up to the maximum, 2904. So how do we troubleshoot this? Well, we know where the problem occurred. Right about here. Right? So let's clear this out. And let's look at TCP.c equal 2904. Okay. So this is when I sent sequence number 2904. I sent 53 bytes worth of data. Then what happened? So let me clear that. So this is the beginning of our problem. Okay. And what do we see? Oh, I'm sorry. Yeah. Describe what we see on the screen. Just kind of think this through.
You've got 300 milliseconds and then you see a retransmission.
300 milliseconds before the retransmission. Okay. What else? I'm sorry? Acknowledgement is 1. What does that mean?
The other guy's not sending data, this is the other direction.
Other guy hasn't sent you any data yet. It's a one-way conversation, which is fine, right? It's like an FTP.
You don't see an back for it, so you're expiring and resending.
Okay, so this is perfect, right? So when does TCP resend data? How do you know to resend the data? I just heard it. Timeouts. What kind of timeouts? So there's, every time TCP does something, timers go off, right? And this is something that's never exposed, and you'll learn over time, different systems have different values. So TCP can't wait forever for an acknowledgement, right? So after a certain time, it assumes, you know what? The packet got lost going the other way, but how come the other guy didn't tell me he lost the packet?
He didn't know he lost the packet.
He never got it. But how does he know he should be expecting that packet? He doesn't. Right? Especially, another clue here is the acknowledgement number is 1, meaning the other guy, the other side, the 192 guy, he doesn't have anything to send you. So in this case, he's just listening for you to send stuff, and when you send stuff, I'll reply back with an acknowledgement. I don't have anything to say to you, so I'm not going to start sending you packets. Okay? And I'm not going to trigger any alarms because for all I know, you're sitting there thinking it was somebody hovering over a mouse click to say, send. Right? I can't differentiate a problem just because there's nothing coming in. But I know from a sender side, a timer went off and I decided to retransmit. Retransmit again, retransmit again, retransmit again, retransmit again. Okay? And then what happens? So let's look at packet number 58. This is the first time that we're seeing a packet coming in from the other side. And what's his acknowledgement number? 2904. Which means from a 192.168 perspective, he's good up to and including what? 2904. I'm good up to that point. So everything after 2904 that 10 dot address sent, he hasn't seen anything yet. What else is different about this packet and this packet? Size. So the first thing that you notice is the size is different. Okay? And what does it say? I'm sorry? There's some data in the packet. Now the other guy is sending me packets. So this is an important clue. Keep in mind what the problem that we're describing. 10 dot is sending traffic to 192. Is it getting there? No. We know for a fact it's not getting there because our retransmission timeouts are occurring and I keep sending and sending and sending and never hear anything back. All of a sudden, 192.168.1.1 sends me an acknowledgement up to and including 2904, and he also sent me some data. So what does that prove?
You're not losing acts that are coming backwards.
I'm sorry?
You're not losing acts that are coming backwards.
You're not losing acts coming from the other side. Technically true, but beyond that, what else do we know? I'm sending you packets, and you have no clue I sent them to you. Because all you told me, the 192 guy, is, I'm good up to 2904. I haven't heard a single thing from you since 2904. May or may not be a problem, I don't know. But between packet number 48 and 57, or 58, the 192 said, you're not sending me stuff, may or may not be a problem, I don't really care, but I have something to send to you, and I'm going to send it to you. Because, notice packet length of 11. So what does that prove? Definitively prove that this is a, what kind of packet loss? One-way packet loss. Packets that I'm sending from 10dot's perspective are not making it to the other side, but 192.168 is able to get through to me. So as network engineers, what should that trigger?
Routing.
Routing?
Firewall.
Natting.
Natting? But why are we throwing these terms out? Not just to throw them out, but what's the end game? Why does routing come into play? Why should you suspect something is going on with routing?
Asynchronous path.
Asynchronous path. Every enterprise network has an asynchronous path, meaning it's redundant. And it's the only field where we use that, redundant to be. It's not redundant like we don't need it redundant. It's redundant like it's duplicate. And it's a good thing. We have redundant paths. We have more than one path. So what's it telling me? That when I go this way, I get blocked. If the other side sent it to me this way, it may or may not have gotten blocked. I don't know. But I do know that this path is good. Right? So you can actually tell, I actually have a Visio tool that maps out Ceph path from a Cisco standpoint, tells me exactly where my next hops are. So when we run it, we notice that when we go out this way, I'm going through the left side, but the return path is coming through the right side. And I only have 2 boxes that are in that path that are redundant. So immediately I was able to say, it was either this box or this box. But because I'm capturing from farther down the stream, I can't positively tell you which one it is. But I do know it's the left side of the equation that's bad. So what did we do? We took a troubleshooting that might have taken a long time. By looking at the packet trace, we know that for fact it's one-way packet loss, and it's the left side of the path that's having a problem. So when we got onto that box, sure enough, we had a soft failure. It was a redundant engine, and it didn't quite fail over, and so it did an alarm because it was a soft failure. Right? The biggest problem to solve in routing and switching is soft failures. When things break hard, redundancy kicks in beautifully. Everything reroutes, life is good. When something gets stuck, and it's lost its mind, and it can't even tell you that it's broken, that's when things start to get black hole and troubleshooting becomes difficult. But this packet trace was taken near the server, the sender, yet we were able to coax the information out of here that most people may not be able to figure out, right? So you can say, oh yes, packet loss, it's retransmissions, etc. But by looking at different parts of the trace, you can start to develop a picture of what may be going on. All right? Any questions so far?
Did that come from us or did that come from the business?
I'm sorry?
Did that one come from us or from the business?
This is one of our subsidiaries.
Okay.
So Bill, he's with our operations team, so he's familiar with this. But it's a subdivision that we have that does trading. So obviously it's high profile. Yes.
When you showed us the analysis flags, I thought there was packet loss in both directions.
Yeah. So let's take a look at that. Actually, let's not take a look at that right now. I'm going to go back to my the most hated words that I saw as students. It can be easily shown that I left as an exercise for the reader. So we'll get back to that when we have time and we can swing back around. Okay? All right, I'm not ignoring you. I'm just, you know, we have a couple other examples that get progressively more difficult. So I just want to make sure we have time. Any questions on this besides the 192 guy? No? Okay. All right. So let's take a look at the next problem. Application is slow. We get this call day in, day out, right? And something is slow, application is slow, it could be the network, it could be congestion, it could be a lot of things. So there are things that you can do with nothing but packet trace to rule out certain things, okay? And your job as doing protocol analysis is to definitively rule out, and this is how I'm going to segue into Dr. McCann's presentation. If you know this part's not even being touched, get rid of it. That's not part of your problem. Concentrate your efforts on something else that you know you can't rule out, right? So let's do that. When an application is slow, what are some of the usual suspects? Immediately you should think about and rule out.
Long round trip time.
Long round trip time. Not a problem in and of itself, but it can lead to other problems, which are bandwidth starvation, okay? We call it BDP, bandwidth delay product, right? Basically you're trickling, you got this massive pipe and you're trickling water through it and you have to wait till it gets to the other side and you're not using your full available bandwidth. Very common problem, okay?
Large
What else?
deltas? Large deltas?
Large deltas is a problem, right? So typically what you do is you scroll down and just kind of scroll through this, and I actually do it at this speed. And what am I doing? I'm just letting my brain pick up on things. So as I'm doing this, what did you guys see? Anybody?
13. Go back up. Go back up.
Go back up.
More.
Right there, one.
Right there. 294.
So there's a huge delta there. That's a problem. What else? Is it always a problem when you see a huge delta?
No.
When is it not a problem?
When the application is
User think time. If I'm sitting there hovering over the mouse, TCP has nothing to do. It may or may not be a problem. You have to actually interview the user to find out. And there are other clues to this. What else is going on? What else do you guys see?
Segment size.
I'm sorry?
TCP segment size.
TCP.
Segment size.
Okay. What do we see about the length here? You're talking about this here, right?
Yeah.
Okay, what does it show? What is it telling us? Anything?
Well, you have one system using an MTU of 1500 byte.
Okay.
The other one, assumably 1400 byte.
Okay, so we got 1400 here, 1500 here, 10 here, 1500, 1500, etc.
I'm talking about the maximum segment size used.
Okay.
So I would look at the three-way handshake to determine if they agree on really the lowest number.
Okay, so here what it's talking about is the maximum segment size. This guy seems to be using 1360. The other guy seems to be using 1460 the default. Okay? But let's say you didn't pick up on that for now. This is a legitimate question. Is it a problem? Right now, do I need to worry about that?
No.
Why do I not have to worry about that as a problem? Because packets are going through. If there was a huge problem, communication would come to a halt. It's not coming to a halt. So I'm going to classify that as something to look at, but maybe not right now. Okay? Things are slow. What do we type? What's the first thing that we always type? And actually, you should have picked up on this already, but I'm going to show it to you. The Wireshark makes it very easy. What do we see?
0 Windows.
Are all Windows updates bad or evil?
Good, good. There's more Windows.
Windows update means what? For example, this guy, what does that mean? My window used to be smaller, but now I'm letting you know I have a bigger buffer. You can send me more information. Is that good or bad? Doesn't matter. Not good or bad. It just means I used up my buffers and now I'm free again. When does it become a problem?
Zero.
And what does zero window tell us? Stop sending me data. I can't deal with this. I don't have buffer big enough to deal with you right now. And it's throwing up a stop sign. Whose problem is that? The network? I'm sorry? The host that sent the zero window is the problem, right? And who sent it? And in my packet tracer, one thing to do is always the client side. Is this a server problem or is this a client side problem? Client side problem, right? So when you first saw this, and I'm going to actually get rid of this. When I got this packet, this is what I did. I was scrolling down, and a block of text scrolled up past, and I said, "Whoa, wait a minute, stop, let me take a look." And I go back, and I did that, right? Now, why don't I just type TCP analysis.flags? Because I'm stubborn. And it's also training. It's training your eyes to pick up on different patterns. Wireshark can't tell you everything that's wrong. Sometimes you have to pick up these patterns on your own. So the more you do it, the better you get at it. So don't always depend on the tool, the analytics of the tool. If you can, and you have the luxury of time, sort by the delta column and scroll down. And see if there are bunches of deltas that are of same value, 200 millisecond, 150 milliseconds, 100 milliseconds. These are signatures that you can use to look at delayed act problems, for example. Okay? So there are different ways to see this problem, to visualize this problem. The first way to do it is you can look at I/O graph. All right? And when you open up the I/O graph, come down to here and click on Advanced. And whose problem did we say? Client-side problem. So whose window size are we interested in? The sender or the client? Or the receiver? The receiver of the data, right? Because the receiver is the guy saying stop. So who was the receiver? I'm looking at only sourced from 192.168.1.1. And what am I looking for? I'm looking at, what am I interested in? Window size. And I'm going to say graph it. What do we see? Typical jigsaw pattern. Up, down, up, down, up, down, up, down. Now, right here doesn't mean that it's at 0. It's kind of like Excel, right? It just means there could be no value. Right? But when you see these peaks and valleys, these jigsaw-like puzzle, it's telling us we have a problem, may have a problem. Another way to visualize this. Let's apply this as a column. Okay, here's the window size, only sourced from 192.168.1.1. And as we scroll down, so far so good. What happened there? So this column right here is the window size. And the fact that window size is going down, is that a bad thing? Not necessarily. I mean, that's what buffers are for, right? It becomes a problem when it becomes so small that I can't receive any more information. That is a legitimate problem. And it has nothing to do with the network. If anything, the network is sending you too much data. Okay? Another way to visualize this is to look at my favorite, which is Stevens graph. And these are things that I do all the time. I look at Stevens graph, and I zoom in, and what do I see here? Stevens graph is nothing more than, over time, how many bytes I've sent. The more steep the slope, the better, because it just means that I'm sending more data over time. When I see patterns like this, though, it concerns me a little bit. Meaning, I have a sudden, large amounts of data going out, and I plateau out, I send, kind of plateau out, send, plateau, send, etc. Right? It's not a, so for example here there's a huge plateau where it's flat. I want to kind of see a consistent line going straight up, ideally. Not everybody will, not every graph will look like this, but ideally that's what you want to see. A 45-degree angle just kind of going slow and steady and increasing, right? More bytes are being sent over time. So this is another clue that I have a window problem. Looking at windows here and scrolling down is another way of saying it. And another way to do it is by doing the charting functionality. Okay? So what was the culprit? AV scanner. It was a script scanning, and this website had a lot of scripts built into it. And the way with JavaScript and etc., it's kind of a choke point. You can't do anything else until that script finishes processing. And when the antivirus is scanning everything else on the web page has to stop. Because even though you may have other TCP sockets that open, etc., with JavaScript, you have to stop and process it and wait till it finishes. So everybody kind of chokes up behind it. The web page slows down, and that was our problem. So what did this tell us? How much time do we have?
20 minutes?
About 20 minutes. Okay, perfect. So this is telling us that it's not a network problem. MSS, it's different. Okay, put that away. Not interesting for now. Packets are getting through. TCP window size, a big problem. But whose fault? Client side. Is it an infrastructure problem? No. And so then you can tell, and you can rule out this massive infrastructure that you have. You can rule out the server, the load balancers, and everything in the middle, and you concentrate your troubleshooting on the client. And that's what we did. And there are only a few things that can mess up communication on the client side. Wrong drivers, virus, and duplex mismatch. That's pretty much it. Is this a duplex mismatch problem?
No.
How do I know that?
It wouldn't work.
It wouldn't work well, but from a packet analysis standpoint, what would I see? Retransmissions, because packets are getting lost. Okay? I don't see that here. What I see is a PC that can't deal with the amount of information that it's getting. So it's either a faulty driver, old, outdated driver, or a machine that can't keep up. Okay? And so by doing troubleshooting on the PC side, we were able to figure out that it was a Mac. It was an antivirus problem. Don't sue me. It was an antivirus problem. All right? Okay, any questions about this one? Again, in and of itself, none of these traces are very exciting or complicated. But what I'm trying to get to, though, is ability for you to kind of divine information that's like circling around these packet traces. Okay, and it's your job to go to that next level and start to pluck this information out and guide people in the troubleshooting. Okay, just from nothing more than packet tracing. All right, so this next example is pretty fascinating. It's titled "Internet is the Internet." So I don't know about you guys, but I do a lot of internet troubleshooting. But if you look at a lot of the carriers, their packet loss SLA on the internet is pretty high. 1 to 2 to 3% packet loss from a contract language is not unusual. It's never really that high. But how do you troubleshoot? How do you begin to troubleshoot the internet? A lot of times you don't. You just punt it and say, I can't help you. It's the internet, right? So this is somebody on my team, Tom. I was busy. I got an email and I said, hey Tom, can you help this guy out? And he called me and said, yeah, it's the proxy in the internet. What do? I said, Tom, just quickly triage it and then punt it. That's exactly what I told him. Triage it and punt it. It's the internet. What can you do? This is okay. So then he calls me back and says, guess what? Not the internet. So this is a problem that we've got. A business unit within City has their own respective customers, right? So my customer is the business units within City. All the different technology, investment banking, City Bank, City Financial. These are my customers. So this customer, a unit of City, dealing with you guys, external customers. And they're saying that this platform is extremely slow. And they're not happy about it. And it traverses the internet. So that's why I said it's the internet, what can you do? But Tom found something that was actually pretty fascinating. And it's a perfect example of knowing what to look for, when to look for, to zero in on a problem. All right, so let's look at the evidence. So there are a couple of things that we learned throughout the session. The red-headed stepchild of protocol analysis is the IT header. It can come into it can be a big clue, kind of like the Blue's Clues thing going on, right? It can clue you in to a big problem. Or it may help you rule things out. So, immediately something should jump out at you when you look at this.
16 millisecond delta on 6?
16 second delta. Is that a problem? Could be. I don't know. Maybe there's think time going on. So what do? We called them up and said, hey, how does your application work? Well, the user clicks on it, gets the data back, and it refreshes the page. Anything else besides once they click? No. Okay, so we ruled out user think time as a problem. Now we have a legitimate problem. But it's the internet. What are you going to do?
Call
Right?
Al Gore.
I'm sorry?
Call Al Gore.
Call.
Al Gore. You got it.
So one of the things, I'm going to kind of digress here and go down to and give you a big clue. So in the IP header, there are a couple of fields that are very important, or can be very important. One of it is IP ID, like we talked about, right? And IP ID helps you identify what? I'm sorry? Whether the system is busy or not. It's a big clue into how many clients is this IP stack servicing from a TCP standpoint, or UDP. Okay? TTL is another one that's kind of interesting. TTL can mean, and it used to, if you read the RFC, it says decrement by clock, 1 second, half second, etc. And then people quickly realized that's not going to work. So they took the easy way out and said every hop on a router decrement the TTL. Why did they do this? They didn't want packets flying around the network forever. So when it decrements down to 0, then you get a port unreachable or TTL expired message, and the packet dies. And then someone cleverly figured out traceroute using TTL expiration. So here are some of the values that you see on a TTL. Why is this important? It can kind of clue you into what systems you may be dealing with. Okay. The other thing too is these numbers should be pretty familiar to you, right? You don't have to memorize it, but it's 30, 64, 60, common numbers, right? Do you see any number here that says 13 or 27, 24, like that? No, right? Nothing exotic there. So let's look at the packet trace. So let's think this through. Fundamentally speaking, right, what's the chief complaint here?
Slow.
It's slow. We already figured out there's no user think time. So this legitimately is a problem. So what happened between packet number 5 and packet number 6? As I'm actually sorry, let me open up the other. So it says sequence number 1, acknowledgement 412. What does that tell us? One more time.
The server 1010 sent something.
Okay, 1010 hasn't sent anything yet, right? I did, however, see 412 bytes from the other guy. Okay? And this is the first time I'm seeing a packet coming in. Okay? So when we first look at this trace, some things you should immediately zoom in on. Here's the SYN and SYNAC. The delta is about 140 milliseconds. I know geographically what I'm dealing with here. It's certainly not New York to Texas. It could be New York to Europe, right? Because 140 milliseconds, as you do more and more of this, you realize North America to Asia Pacific, 250, 300 milliseconds typically. To Australia, 275, 300. Okay, these are some numbers that you kind of pluck out over time. So I'm dealing with, all right, this is North America customer talking to probably somebody in Europe. Okay, I don't know that for a fact. Well, I can't do it because in real IP, I could just go to Aaron or write and type it in, right? So I knew that this was EMEA, but I didn't have to actually. I don't need Aaron or Wright to tell me that. I can tell just by looking at the round trip latency. Okay, what else? Could something have happened from here to here? I'm capturing it from 192 side. Do I know if 10's been trying to send me packets? For all I know, this could be the mirror image of the earlier problem where somebody was sending me packets and it just got stuck, black hole. How do I know if this between here and here, that this guy wasn't sending me packet after packet after packet after packet trying to talk to me?
Was it the IP?
All right, so let's do that. And what is that going to tell us?
How busy the client system?
I'm sorry?
If we're looking in this direction, how busy the NIC is on the client system that's sending you the data.
Okay, so I'm going to add the IP ID here, and something should become immediately apparent. Or maybe not.
Is that expect?
Window size? Oh, I'm sorry. sorry.
So you can already have it.
Oh, I did have it right here. Okay.
The sequential.
You didn't send us anything.
What happened between this packet and this packet?
Nothing.
Was there a retransmission going on?
No.
Was the 10-dot guy trying to reach out through the cloud and touch me? No. Is that 10-dot server particularly busy? So this is a commercial server with a vendor doing nothing but talking to me. What are the chances that a site like Amazon has no other customers but me? And this is what it's telling me.
Getting good service.
You're sitting, damn it. Dedicated server for one guy. So actually, there could be a proxy in the middle, right? Even then, IP stack tends to be what? Communal, right? Even on a proxy and a load balancer, IP stack is common to multiple TCP stacks. It's like a funnel, right? So what do I know from this trace just by looking at the IP ID field?
You're not dropping packets.
I'm not dropping packets. There was nothing going on between this packet and this packet. So whose fault is it? The server. How do I know that? Because at this point in time, the server was doing nothing. He wasn't talking to another customer, another application. Nothing was going on this server between this packet and this packet. And my proof positive, I'm sorry, this packet and this packet, and my proof positive is that IP ID incremented by just 1. Nothing was going on. This is all server processing time. Okay? So once you're armed with that knowledge, what do? You call them up. Hey, your server's broken. It's not the internet, right? And when we called them, the irony was, we had configured to talk to its old UAT system, meaning its test system. So they migrated off this platform and went production somewhere else, somewhere close, actually. And we didn't get that memo, apparently, and we were using the old system that no one else was using. So when we called up the vendor, they said, what address are you going to? I said, you know what? We migrated off that months ago. You should be using this system. So all that time, we were paying needless delay, and it took someone to finally pick up the phone and say, something is wrong, and I give Tom from my team credit. I punted it and said, it's the internet triage it. He did. But when he looked at this, most people will say, it's either packet loss happening from here to here, or it's a delay, and maybe would have punted it. But what he did was, he looked at the IP ID field and TTL to figure out what was happening. And why is TTL important in this case? What's my TTL here? 62. 64 is a common number, right? As you showed, 60 is a common number. So if I'm thinking 64, maybe 128, I'm probably, if it's 64, I'm just 2 hops away from the capture point, from the server. Okay, so when 192 sent it out, he probably started out with 64. Okay, I know it's not 128 because this 192, 168 is on my network. And I know it doesn't take 64 hops to get out to the internet. I know that because my network, right? So I'm probably just 2 hops away. What about this guy? What's his TTL? 44. So he probably started out around 60 something and went through 20 different hops to get to me. Nothing unusual. Hop counts mean nothing from a performance standpoint in modern day network. Just to get out of my data center, I can go through 8 hops. Just to get out of my data center. It doesn't mean anything because it's all hardware switch. Back in the days when packets were process switch, TTL did mean something because the routers were literally could add milliseconds in packet processing time. Here, they're done in microseconds, and so it's nothing to worry about typically. So what's the lessons learned here? Look at the IP ID field, and before you punt, do a quick triage. Don't throw away the IP header. I know it's not exciting, and most people that do Wireshark analysis are always in this TCP field. But IP ID has a wealth of information that you can use to rule things out. Okay? Any questions so far? Okay, I think my time is up, is it not?
7 minutes?
Oh, 7 minutes, okay. So let me go back to, by the way, any questions here about Wireshark using the column? The one other thing that I want to show you before we get to some of the things that I do, I use profiles here. And the reason why I use profiles is because when I'm troubleshooting, I want to be able to see different layout quickly, back and forth. And one thing that I do have is absolute date. So why is this important? So a friend of mine is in med school, and the analogy here is this. She was doing going through, not nuclear medicine, but x-ray, looking at x-rays and whatnot. And the exam was, first thing you do when you look at an x-ray, what do you do? I'm sorry?
When was it taken?
When was it taken and who was it taken for, right? Because the worst thing you want to do is look at the wrong x-ray for the wrong patient. So the first thing I do, I look at the absolute time date stamp. Make sure that somebody didn't give me the wrong packet trace. Nothing ticks me off than spending 2 hours saying, I'm not seeing anything here. Oh yeah, sorry. GMT offset, you're 2 hours away from the problem. So I quickly look at absolute time. Now I can do that by looking and changing the time field here, right, the view. But I just got used to doing it this way, so this is what I do. Some of the other thing that I do one where I just have the time, because the reason for the absolute time and not the date is once I verify the time, some users report problems in real time, like at 9:15, right? Or when you're working with a chronic problem, you train users to say, hey, look at this clock here. When you have a problem, see what time that is, because for the most part, we're synchronized. And at least that gets me in the right ballpark. I may have 100,000 packets in a second, but it's better than 1,000,000 packets. So at least get me in the right ballpark. Okay, so this real time, the timestamp here can be important. And actually in my next session that I'm doing, it was one of the first clues that helped that when the user said, I had a problem at 9:17, it got us there quickly and we were able to find the root cause. Okay. The other thing that I do is, I don't have it here because this is the new Windows 7 build that I have. I haven't had time to do it. Is I turn on relative sequence numbers, and so the reason why relative sequence numbers are nice is that if you haven't seen it, TCP sequence numbers are what kind of numbers? It's a 32-bit number, pretty large. So instead of looking at 412 versus 1, if I look at a real TCP real sequence number, that 412 just became this number. And of course there are no commas here, so you have to sit here and go 774, 740, 1.2 million, 12 million, 1.2 billion, I don't know. No commas. My pet peeve. When you're looking at interface stat on a router, no commas. You have to literally sit there and go, okay, is it 12 million, 12 billion, 120 million? So it's difficult. Your brain has hard time processing these large numbers, so relative sequence numbers are good to use. When should you not use relative sequence numbers? Capturing at different points, perhaps. Different start times, because relative means just that. It's relative to where you started your capture. may not line up. So when you're looking at specific gaps in transmission, sometimes it's better to be sure by going to real sequence numbers and looking at it from both sides. Okay? Also, if there's NAT in the middle, sometimes, depending on how it's being NATed, sequence numbers may get jumbled, it may survive, IPID may survive. So over time, you're going to develop these practice and patterns and habits where, even though I know it's going through a firewall or a NAT, you're going to realize, oh, you know what, big IP tends to only munge the source sequence number, not the destination, or it maintains the IP ID, and you'll start to pick up on these combinations to help you troubleshoot. Okay? So again, nothing that I showed you in this class was really elaborate or difficult problem. What's difficult is trying to get as much information out of it, and if you know what you're doing and you practice, you can rule things out. It's all about dividing and conquering. Right? We all have a lot of things to do. Divide and conquer. Reduce that problem set to something that you know for sure you should concentrate on, and throw out all the other clutter. Okay? And the more you use this, the more your brain's going to be able to quickly rule things out, and they just kind of disappear in the background. And different problems it'll be like a shining beacon, if you will. Okay? And that's kind of what you need to do, and you can only do that by practicing. Okay? That's all I have. Any questions for me? Yes? Okay, so what other tools do I use? We actually use different tools from both Pilot. When I'm dealing with huge trace file, Pilot, if you haven't seen it, I encourage you guys to download Pilot demo and take a look. It's the GUI version of the Pilot, the way the concept of dragging and dropping these analysis to the packet trace file is phenomenal, right? So we also use OpNet, ACE Analyst. A lot of the problem though is we all suffer, or all these tools suffer from garbage in, garbage out. And so you really do have to be diligent about, it's nice reports that gets, it spits out beautiful looking reports, but it may all be based on false information and it turns out to be useless. Okay, so it's your job as analysts to rule that out and make sure that the report that it's spitting out is in fact factual and correct. Okay? Anything else? Yes?
Where do you pull the packets from? Do you pull those from the same place or off the servers?
So at City we have multiple locations. We sometimes we put capture agents on PCs that we control. Sometimes it's TCP dump or snoop or IP trace. Sometimes it's a sniffer that we have in a common location that we span the ports to. So it depends on the situation. Okay. We have these sniffers deployed throughout the data centers that we move around and take packet captures as required. But oftentimes, Wireshark at the client, at the proxies, firewalls, they all have TCP dump built in, right? So those are good places to start. And in most cases, you don't need full packet captures. So don't get in the habit of doing full packet captures, because all you're going to do is waste space. Most TCP analysis don't require full packets, okay? Unless you're doing applicational choice.
The sniffer that you mentioned, is it like data recorder or just like a point and shoot device?
Yes, it's a big sniffer. It's a constant running with huge terabytes of data. Shark Appliance is one. There are other vendors that have, big honking sniffers, if you will. Some people use laptops with Wireshark running all the time, right? So it depends on your budget and how creative you want to be. Anything else, guys? Okay, thank you very much. I'm going to hope that this worked. Thinking back now, maybe I should have stopped and double checked.